Welcome to Finite Math, Chapter 3, Section 2, Trig Identities and Equations. So, for these problems, we need to prove that each equation is an identity. In order to prove that, we're only allowed to change one side of the equation. So, right now, I'm going to start by distributing tangent over here and seeing what happens. I get the tangent times the cotangent, which we know is going to be 1 because they're in reciprocal functions to each other. And tangent times tangent would be tangent squared. And we're not allowed to change the other side of the equation, so we'll just keep it as equals secant squared. Now, again, we said that tangent times cotangent is 1 plus the tangent squared of x equals secant squared of x. And that was one of our trig identities. That was one of the rules, where 1 plus the tangent squared of x is the same thing as secant squared. And the proof of the identity is when you show that something equals itself. So we do have to end with the secant squared of x equals the secant squared of x. And that's number 2. If we look at number 6 next, we have the cosine squared of theta plus the tangent squared of theta times the cosine squared of theta equals 1. So one of the ways that we can oftentimes start problems like this is we can just turn everything into terms of sine and cosine if we want to. So we have the cosine squared of theta plus the sine squared of theta over the cosine squared of theta times the cosine squared of theta. And now that will equal 1. And we might notice that because we are dividing by the cosine squared and multiplying by the cosine squared, they cancel each other out. So now we have that the cosine squared of an angle plus the sine squared of an angle equals 1. And that is our main trig identity. So 1 equals itself. And we have now proven that this is an identity. The next one, number 12, involves a little bit of factoring. So we have the secant to the fourth of t minus the tangent to the fourth of t equals 1 plus 2 times the tangent squared of t. So this one might take a little bit of space here. But secant to the fourth minus tangent to the fourth looks like a squared squared minus b squared squared, because squared squared is to the fourth, and we can make that look like an a squared minus b squared situation, which would become a plus b times a minus b, where right now a is the secant squared of t and b is the tangent squared of t. So we can turn this into, we can factor it to the secant squared of t plus the tangent squared of t times the secant squared of t minus the tangent squared of t equals, and I kind of ran out of space for right now, so right now I'm just going to say equals 1 plus 2 times the tangent squared of t. I will add that piece back in once I have space. So again, if we look at our trig identities, the secant squared of t minus the tangent squared of t really equals 1. So we have the secant squared of t plus the tangent squared of t times 1 equals 1 plus 2 times the tangent squared of t. So we're actually going to use the same rule to our advantage again in a moment. If we distribute the 1, nothing really changes, so we get that the secant squared of t plus the tangent squared of t equals 1 plus 2 tangent squared of t. Now, what we're looking for, since we already have 1 tangent squared of t, but we need 2 of it, we need a way to turn secant squared into tangent squared. And since secant squared minus tangent squared equals 1, we can say that secant squared equals 1 plus the tangent squared if we were to solve that and use one of the other rules. So we can actually take this secant squared and turn it into 1 plus a tangent squared of t plus the other tangent squared of t that we've already got equals 1 plus 2 times the tangent squared of t. And then we can simplify those. A tangent squared of plus another tangent squared makes 2 of the same thing, 2 tangent squared. Sorry about the glare here. So we have that 1 plus 2 of the tangent squareds of t, and these equal 1 plus 2 times this tangent squared of t, which is the same thing, so this is an identity.